In this video, we're going to look at how de Moivre's theorem can be used to determine both powers and roots of complex numbers. First of all, though, we need a little bit of a recap from Unit 1. If we have z is the complex number a plus ib, then the modulus of z is simply the length of the line on the Argand diagram that joins the point representing z, that is the point AB, to the origin. So the modulus of z is simply the square root of a squared plus b squared. The argument of z is the anti-clockwise angle which OA makes with the positive real axis. The argument of a complex number z is traditionally given as an angle in radians, and there are two conventions that are used. Either the argument of z is given between minus pi and pi, or alternatively the argument of z is given between 0 and 2 pi. Usually in an exam question, if it matters which convention is going to be used, the question will make it clear. We also know that if the modulus of z is equal to r and the argument of z is equal to theta, then we can write z as being r times cos theta plus ir sine theta, or equivalently we can write z as being r times cos theta plus I sine theta. Now we also need to remember some results about power series that come in Unit 4, this unit. And that is the results for the power series of e to the x. That is that e to the x is the same as 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4, and so on. That cos x is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6, and so on. And that sin x is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7, and so on. And that each of these series is valid for all real values of x. Now, what happens if we put x equals I theta into the expansion for e to the x? Well, if we do that, we've got e to the I theta is going to be 1 plus I theta plus 1 over 2 factorial I theta squared plus 1 over 3 factorial I theta cubed plus 1 over 4 factorial I theta to the power 4, and so on. Now, if you think about that, I squared is minus 1. I cubed is the same thing as minus I. I to the 4 is the same thing as 1. I to the 5 is the same thing as I to the 6 is the same thing as minus 1, and I to the 7 is the same thing as minus I. So we've now got e to the I theta is 1 plus I theta minus 1 over 2 factorial times theta squared minus 1 over 3 factorial times I theta cubed plus 1 over 4 factorial theta to the power 4, and so on. And if we split these up into the real terms and the imaginary terms, then the real terms that we've got are 1 minus 1 over 2 factorial theta squared plus 1 over 4 factorial theta to the 4 minus 1 over 6 factorial theta to the 6, and so on. Whilst the imaginary terms are I times theta minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the power 5 minus 1 over 7 factorial theta to the power 7. And if we look carefully, the real terms are precisely the terms which make up the series for cos theta, and the imaginary terms are precisely the terms that make up the series form for sine theta. So we've now obtained the important result that e to the I theta is the same thing as cos theta plus I sine theta. So if we know that modulus of z is r and argument of z is theta, which we often write in abbreviated form as z equals r comma theta inside square brackets, then we can write z equals r cos theta plus I r sine theta, which is the same thing as r times cos theta plus I sine theta, and we have just seen that that is the same thing as z equals r e to the I theta, because we know that e to the I theta is precisely cos theta plus I sine theta. Now, let's start making use of Demoivre's theorem, and we're going to make use of it to find powers and roots of complex numbers in this video. So, let's suppose that we know that mod z equals r and arg z equals theta. Then we already know that z is equal to r cos theta plus I sine theta. In which case, if n is an integer, then z to the n is r times cos theta plus I sine theta all to the power n, which is the same thing as r to the n times by cos theta plus I sine theta to the power n, which is, by Demoivre's theorem, the same thing as r to the n times by cos n theta plus I sine n theta, because Demoivre's theorem says that for a positive integer n, cos theta plus I sine theta to the power n is cos n theta plus I sine n theta. And that in turn means that the modulus of z to the n is going to be r to the n, and the argument of z to the n is going to be n theta. So we've got a shorthand for this, that if we know that z is given by r theta in square brackets, which means that the modulus of z is r and the argument of z is theta, then Demoivre's theorem is telling us that z to the n is going to have a modulus of r to the n and an argument of n theta. Alternatively, if we write z as being r e to the I theta, and n is an integer, then we've got z to the n is going to be r to the n e to the I n theta. So, as an example, let's find the value of minus 1 plus root 3i to the power 20, giving the answer in the form p plus iq. If we're going to make use of the results we've just set up, we're going to need to turn the complex number minus 1 plus root 3i into its modulus argument form. So, minus 1 plus root 3i, the modulus of z is going to be the square root of minus 1 squared plus root 3 squared, which is the square root of 4, which is 2. To find the argument of z, it's a good idea in this case to find alpha first of all. And if we look at the triangle that we've got, we know that tan alpha is root 3. So therefore alpha is 60 degrees, or, since we should be using radians, pi by 3. So the argument of z is going to be pi minus alpha, which is pi minus pi by 3, in other words, 2/3 pi. So we can say that z is the complex number whose modulus is 2 and whose argument is 2 pi by 3. Or we can say that z is 2 times by e to the I 2 pi by 3. Now at this stage then, we need to remember the important result that if z has modulus r and argument theta, then z to the n has modulus r to the n and argument n theta. So we can certainly say that z to the 20 is going to have modulus 2 to the 20 and argument 20 times 2 pi by 3. In other words, it's got modulus 2 to the 20 and argument 40 pi by 3. Or we could write that as being saying that z to the 20 is 2 to the 20 e to the I 40 pi by 3. Now, as an argument, 40 pi by 3 is the same thing as 12 pi plus 4 pi by 3. Now, 12 pi is 6 complete circles. So it's 6 complete circles, which is the same thing as doing nothing at all, plus 4 pi by 3. So an argument of 4 pi by 3 is an argument of 40 pi by 3 is exactly the same as just an argument of 4 pi by 3, because 12 pi just represents 6 complete circles. So we can say that z to the 20 is actually 2 to the 20 as its modulus and 4 pi by 3 as its argument, which means in turn that I can say now that z to the 20 is 2 to the 20 times by cos 4 pi by 3 plus I times sine 4 pi by 3. Cos of 4 pi by 3 is minus a half. Sine of 4 pi by 3 is minus root 3 upon 2. So I've got z to the 20 is minus 2 to the power 19 minus 2 to the power 19 times by root 3 times I. And that is a heck of a lot quicker than trying to multiply out using Pascal's triangle, minus 1 plus root 3i to the power 20. For our second example, we're going to try and find all of the cube roots of 2 minus 2i, giving the answers again in the format p plus iq. Now again, we're going to start this by turning the complex number 2 minus 2i into its modulus argument form. So 2 minus 2i has got a modulus of 2 squared plus minus 2 squared all square rooted, so it's got a modulus of root 8. And the argument in this case, well, if we look at the triangle we've got there, we've got tan alpha is equal to 1, so alpha must be pi by 4. So we can say that the argument of 2 minus 2i is either minus pi by 4, so we can do it as a clockwise turn of pi by 4, which means it's an argument of minus pi by 4, or we can say it's an anti-clockwise turn of 7 pi by 4. It doesn't matter which format we give at this stage for the argument of 2 minus 2i. So we can say that 2 minus 2i is the same thing as the complex number with modulus root 8 and argument 7 pi by 4. Okay, now remembering that, what we're now trying to do is we're trying to find the solutions of the equation z cubed equals 2 minus 2i. And we're going to suppose that z has got a modulus of r and an argument of theta. Now, if z has a modulus of r and an argument of theta, and recalling our basic result, we know that if n is a positive integer, then z to the n has a modulus of r to the n and an argument of n theta. So, in particular, z cubed is going to have a modulus of r cubed and an argument of 3 theta. So what we want is we want r cubed, the complex number with modulus r cubed and argument 3 theta, to be the same as the complex number with an argument of a modulus of root 8 and an argument of 7 pi by 4. Now, looking at this as two separate equations, first of all we want r cubed to be equal to root 8. So in other words, we want r to be the cube root of root 8, and the cube root of root 8 is root 2. So we know that r has got to be root 2. We also want 3 theta to be equal to 7 pi by 4. And that fairly obviously gives me theta equals 7 pi by 12. But, and this is important to realise, we could have 3 theta equals 7 pi over 4 plus 2 pi. So that's 7 pi by 4 plus a full circle of 2 pi. Or we could have it being 7 pi by 4 plus 2 full circles of 2 pi. Or we could have 7 pi by 4 plus 3 full circles of 2 pi. In other words, we could have 3 theta equals 7 pi by 4, or 7 pi by 4 plus 2 pi, which is 15 pi by 4, or 7 pi by 4 plus 2 circles of 2 pi, which would be 23 pi by 4, or 7 pi by 4 plus 3 circles of 2 pi, which would be 31 pi by 4, etc. So now, dividing through by 3, we have theta equals 7 pi by 12, or 15 pi by 12, or 23 pi by 12, or 31 pi by 12, etc. But, to stop, 31 pi by 12 is actually exactly the same as 2 pi plus 7 pi by 12. So as an argument, 31 pi by 12 represents a full circle plus 7 pi by 12. In other words, it's exactly the same as having an argument of 7 pi by 12. So that's merely a repetition of the first one. The next one along would be a repetition of the 15 pi by 12. The next one along would be a repetition of the 23 pi by 12. So all we will get afterwards is a whole series of repetitions. So we have the cube roots of 2 minus 2 are the complex numbers. First of all, the one with modulus root 2 and argument 7 pi by 12. Then modulus root 2 and argument 15 pi by 12. And then finally root 2 and argument 23 pi by 12. And putting these back into their p plus iq formats, we've got the first root is going to be root 2 times by cos 7 pi by 12 plus I sine 7 pi by 12, which turns out to be minus 0.366 plus 1.366 times I. The second one turns out to be minus 1 minus I. And the final one turns out to be 1.366 minus 0.366 I. So we've managed to find the 3 cube roots of 2 minus 2i. For the next example, we have to express the complex number minus 64i in the form re to the I theta, where r is bigger than naught and theta lies between minus pi and pi. We then have to solve the equation z to the 6 plus 64i equals naught, giving the answers in the format re to the I theta. So, minus 64i has got a modulus of 64. Now that should be clear because the point representing minus 64i is clearly 64 units away from the origin. The argument of minus 64i, well, we can either say we've got to go 3 pi by 2 in an anti-clockwise direction or pi by 2 in a clockwise direction. Since we were being asked for the argument between minus pi and pi, then we need to say the argument in this case is minus pi by 2. That is a turn of pi by 2 in the clockwise direction. So we know that the modulus is 64, the argument is minus pi by 2, so I can say that minus 64i is the same thing as 64e to the minus I times pi by 2. If the complex number with modulus r and argument theta is a solution of the equation z to the 6 plus 64i equals 0, then I want z to the 6 has got to equal minus 64i. Remember that I know that if z has modulus r and argument theta, then z to the n has got modulus r to the n and argument n theta. So z to the 6 can be written as the complex number with modulus r to the 6 and argument 6 theta. And I want that to be equal to the complex number whose modulus is 64 and whose argument is minus pi by 2. So looking at the moduluses first of all, I know that I want r to the 6 has got to equal 64. In other words, r must equal 2. And considering the arguments, we want 6 theta to be equivalent to minus pi by 2. But an argument of minus pi by 2 is the same thing as an argument of minus pi by 2 plus a complete circle, in other words 3 pi by 2, or minus pi by 2 plus 2 complete circles, which will be 7 pi by 2, or minus pi by 2 plus 3 complete circles, which will be 11 pi by 2, or minus pi by 2 plus 4 complete circles, which will be 15 pi by 2, etc. So dividing through by 6, we obtain theta must be minus pi by 12, or 3 pi by 12, or 7 pi by 12, or 11 pi by 12, or 15 pi by 12, or 19 pi by 12, or 23 pi by 12, etc. Now, we're looking for arguments that lie between minus pi and pi. An argument of 15 pi by 12 doesn't. But 15 pi by 12 is the same thing as 15 pi by 12 take away 2 pi, in other words, minus 9 pi by 12. 19 pi by 12 is the same thing as 19 pi by 12 take away a full circle of 2 pi, which is minus 5 pi by 12. And 23 pi by 12 is the same thing as 23 pi by 12 take away a full circle, which will give me minus pi by 12. But minus pi by 12 we've already picked up, so we can forget that one altogether. So I have now got 6 possible values for theta. namely minus pi by 12, 3 pi by 12, 7 pi by 12, 11 pi by 12, minus 9 pi by 12, and minus 5 pi by 12. Which means that I now know that the solutions of the equation have all got modulus 2 and have these 6 different possible values for theta. So in r e to the I theta form, the solutions are 2e to the minus I pi by 12, 2e to the I pi by 4, because 3 pi over 12 cancels to pi by 4, 2e to the I 7 pi by 12, 2e to the I 11 pi by 12, 2e to the minus I times 3 pi by 4, and 2e to the minus I times 5 pi by 12. And we now move on to our final example, in which we start by finding all of the roots of the equation z to the 5 equals 243. We've got to sketch these roots on an Argand diagram, and we then have to factorize z to the 5 minus 243 as the product of a linear factor with real coefficients and 2 quadratic factors, each with real coefficients. So, to begin with, the complex number 243 has got modulus 243 and argument 0. If z, which is equal to r theta, is such that z to the 5 equals 243, then I must have r to the 5 theta, that's the modulus of z to the 5 and the argument of z to the 5, must be equal to the complex number whose modulus is 243 and whose argument is 0. So, first of all, I must have r to the 5 equals 243, which gives me r equals 3. And secondly, I must have phi theta is 0, or it could be 0 plus 2 pi, or 0 plus 4 pi, or 0 plus 6 pi, or 0 plus 8 pi, or 0 plus 10 pi, etc. Which means that theta must be 0, or 2 pi by 5, or 4 pi by 5, or 6 pi by 5, or 8 pi by 5, or 10 pi by 5, etc. But 10 pi by 5 is just 2 pi, and an argument of 2 pi is exactly the same as an argument of 0. So we can delete that solution, and all the subsequent ones will just be repeats of the earlier ones. So, in modulus argument form, the possible solutions are the complex numbers whose modulus argument form are 3 0, or 3 2 pi by 5, or 3 4 pi by 5, or 3 6 pi by 5, or 3 8 pi by 5. Now, if we call those solutions Z0, Z1, Z2, Z3 and Z4, first of all notice that they've all got modulus 3, which means that the roots lie on a circle of radius 3 and centre the origin. Notice also that the arguments of the adjacent roots differ by 2 pi by 5, which means that the roots are evenly spread around the circle. And if we put those two facts together, that means that we've got the polygon forms a regular pentagon, centre the origin, with the vertices lying on the circle of radius 3. It's worth noticing at this point that we have found the roots of the equation z to the 5 minus 243 equals 0. And because this is a real polynomial, that is, all the coefficients in the equation are real numbers, the complex roots must appear as complex conjugate pairs. And we can see that from the diagram that Z1 and Z4 a complex conjugate pair, and Z2 and Z3 form a complex conjugate pair. So, there are 5 roots of the equation z to the 5 equals 243, or equivalently, there are 5 roots of the equation z to the 5 minus 243 equals 0. So the factor theorem tells me that z to the 5 minus 243 must equal z minus z0, z minus z1, z minus z2, z minus z3, z minus z4, all multiplied together. Z0 is 3. So I have straight away got a factor, and this is my real factor, of z minus 3. So I now know that z to the 5 minus 243 must be equal to z minus 3 times by z minus z1, z minus z4, z minus z2, z minus z3. Now you'll notice I've changed the ordering slightly, and the reason for that is I've paired together the complex conjugate pairs. So if I have a think for a moment or two about z minus z1 times by z minus z4, I know that z1 is 3e to the I 2 pi by 5, which is the same thing as having a modulus of 3 and an argument of 2 pi by 5, and that z4 is the complex number with modulus 3 and argument 8 pi by 5, or equally well, argument minus 2 pi by 5. So I can write z4 as being 3 times e to the I minus 2 pi by 5. So if I have a look at z minus z1 times by z minus z4, I've got z minus 3e to the I 2 pi by 5 times by z minus 3e to the minus I times 2 pi by 5. Multiplying that out, I get z squared minus 3 times e to the I 2 pi by 5 plus 3 times e to the minus I 2 pi by 5 times by z, add 9. E to the I 2 pi by 5 is cos 2 pi by 5 plus I sine 2 pi by 5. E to the minus I 2 pi by 5 is cos of minus 2 pi by 5 plus I sine minus 2 pi by 5. So I've got all of that times by the 3 times by the z. I've still got the plus 9 on the end. Cos of minus 2 pi by 5 is the same as cos of 2 pi by 5. Sine of minus 2 pi by 5 is the negative of sine of 2 pi by 5. So the sine 2 pi by 5 I terms just cancel each other out. The cos ones are identical to each other, so altogether I've got z squared minus 6 lots of cos 2 pi by 5 times by z, add 9. In an exactly similar way, z minus z2 times z minus z3 gives me z squared minus 6 cos 4 pi by 5, z plus 9. So, putting these results all together gives me the full factorization of z to the 5 minus 243 as being z minus 3, then the z minus z1 times z minus z4 becomes z squared minus 6 cos 2 pi by 5 times z plus 9, and the z minus z2 times z minus z3 becomes z squared minus 6 cos 4 pi by 5, lots of z, add 9. So I've got a factorization of z to the 5 minus 243, which has got a real linear factor, a real quadratic equation, a real quadratic factor, and another real quadratic factor, which is exactly what I was trying to achieve. Finally, we just want to set up a general case for finding the nth roots of an arbitrary complex number. So if I want to find the nth roots of the complex number with modulus r and argument alpha, then what I'm trying to do is I'm trying to solve the equation z to the n equals the complex number with modulus r argument alpha, or the complex number re to the I alpha. If we suppose that z has modulus r and argument theta, then de Moivre's theorem tells me that z to the n is going to have modulus r to the n and argument n theta. So what I require is the complex number with modulus r to the n and argument n theta has got to equal the complex number with modulus capital R and argument alpha. So that means that I've got to have little r to the n has got to be equal big R, so little r has got to be the nth root of big R. And it also means that I need n theta to be alpha, or alpha plus 2 pi, or alpha plus 4 pi, or alpha plus 6 pi, all the way along, and keep going. Dividing through, that gives me theta must be alpha over n, or alpha plus 2 pi over n, or alpha plus 4 pi over n, all the way along to alpha plus 2n minus 1 times pi over n. But the next one along, alpha plus 2n pi over n, well 2n pi divided by n is just a full circle of 2 pi. So that would simply be a repetition of the very first solution that we had. So we can delete that one. The next one along is simply going to be a repetition of the second solution that we originally happened. So we can delete that one. And all the subsequent ones are just repetitions of the earlier ones. So we've got theta has got to take the form alpha over n, alpha plus 2 pi over n, alpha plus 4 pi over n, and the final new one is alpha plus 2 lots of n minus 1 pi, all divided by n. In other words, we can say that theta is alpha plus 2k pi divided by n for k equals 0, 1, 2 all the way up to n minus 1. So the nth roots of the complex number with modulus r and argument alpha are given by complex numbers of the form r to the 1 over n, so that's the nth root of capital R, and then the arguments take the form alpha plus 2k pi divided by n for values of k which take the values 0, 1, 2 all the way up to n minus 1. Now we'll find this result useful in a later video. So that concludes our look at powers and roots of complex numbers. In the next video, we'll be looking at how we can use de Moivre's theorem to help us obtain trigonometric identities.